Today, we're diving into one of the biggest and honestly weirdest questions in all of science. It all comes from a famous paper with a fantastic title, The Unreasonable Effectiveness of Mathematics.
Our guide on this journey is the Nobel Prize winning physicist Eugene Wigner. Back in 1960, he wrote about a mystery that feels almost supernatural, and he kicks the whole thing off with a really strange little story.
So the story goes like this. A statistician is trying to explain his work on population trends to a friend. He shows him all these complicated formulas, and the friend spots a familiar symbol, pi. You know, pi. He asks what it is, and the statistician says, "Oh, that's the ratio of a circle's circumference to its diameter." The friend is just completely baffled, saying, "Wait, what do circles have to do with population growth? That makes no sense." And you know what? He's got a point. It's a bizarre, totally unexpected connection.
And that right there is the million-dollar question. What if it does? What if the purely abstract world of math, of circles and numbers, somehow has everything to do with the real, messy world of people and planets and galaxies? To really get our heads around just how strange this is, we've got to do what Wigner did and define our terms.
Okay, so first up, math. According to Wigner, math isn't the study of nature. Not at all. It's a world that is completely invented by us, by the human mind. It's basically a game with concepts and rules that we made up.
You know, mathematicians create things like complex numbers, not because you can find one in the wild, but because the ideas themselves are elegant and beautiful. They build these intricate structures for their own sake. And honestly, as Wigner points out, the fact that this whole invented universe of math doesn't just collapse into a pile of contradictions is a miracle in itself.
All right, so in the other corner, we have physics. And physics is the complete opposite. It's not about invention, it's all about discovery. The physicist looks at this incredibly complex, chaotic world and tries to find the patterns, the laws of nature that are hiding in plain sight. Just think about Galileo. He drops two different rocks and they hit the ground at the same time. Boom, that's a law. But notice how specific that is. It's an if-then statement. If you drop the rocks, then this will happen. It doesn't say anything about why rocks exist or why gravity works. Physics finds these little threads of order in the chaos, and those threads let us predict what's going to happen next.
So you see the problem, right? We've got two completely separate projects here. Math is this abstract, beautiful game we made up. Physics is our attempt to describe the real world we observe. Logically, there is no reason why one should be useful for the other. And yet,
They are connected, and not just a little bit. It turns out the language of mathematics is the perfect, unbelievably accurate way to describe the universe. This is what Wigner calls the unreasonable effectiveness. So let's look at the evidence, because it's pretty staggering.
First up, a classic you all know, Newton's law of gravity. It's maybe the most famous scientific law ever, and it's a perfect example of what we're talking about.
Now, you'd probably think Newton had mountains of perfect data to work with, right? Wrong. Wigner makes it clear that the law was based on surprisingly little data, and the data he had wasn't even that precise. Plus, the very idea of action at a distance, that the sun could pull on the Earth from millions of miles away, was a totally wild and spooky concept at the time.
And here's where the language part comes in. Newton didn't just say stuff falls. He used the language of calculus, a concept called the second derivative, to describe exactly how gravity works. Now, this is not some simple idea you get from just watching an apple drop. It's a complex, abstract piece of math.
So what happened when we took this abstract math based on very little data and applied it to the cosmos? Well, it turned out to be accurate to a degree that is just mind-blowing. The margin of error is less than a 10,000th of a percent. I mean, that's an accuracy Newton couldn't have even dreamed of. The math didn't just describe what he saw, it described a deep truth about the universe itself.
Okay, if you thought that was wild, hold on. Let's take it up a notch and go from the massive scale of planets to the impossibly tiny world of quantum mechanics. This is where the story gets almost unbelievable. Long before anybody knew what an atom really was, mathematicians had invented a whole branch of abstract math called matrix mechanics. They did it just for fun, really, because it was logically beautiful. Decades later, physicists are tearing their hair out trying to describe the bizarre quantum world, and they stumble upon this old math, and it turns out to be the perfect language for the job. When they used it to predict the behavior of a helium atom, the results matched experiments with an accuracy of 1 part in 10 million. I mean, Wigner's own words really say it all here. The physicists got way more out of the math than they ever put in.
The math wasn't designed for the problem, it was just waiting. It's like finding an old, ornate key in your attic and discovering it perfectly unlocks a door to a new reality you never knew was there.
So this incredible success, this miracle, leads us straight into a massive philosophical problem. It's the very thing that makes modern science possible, but it's also a kind of nightmare for anyone who wants to know why it works.
And that is the fundamental question, isn't it? Why? Why on earth is the universe built in a way that allows our made-up games of logic to describe it with such stunning precision? We still have no idea.
And this leads to a huge dilemma for physicists. On the one hand, there's what Wigner calls an article of faith, this deep belief that all our successful theories, like relativity and quantum mechanics, will one day merge into a single beautiful theory of everything. But then there's the theorist's nightmare. What if they don't? What if we just keep finding different mathematical tools that work perfectly for their own little patch of reality, but never ever connect into one single truth?
So you see the problem. We have no idea why our theories work so well. And their incredible accuracy doesn't actually prove that they are the final, ultimate truth. It just proves they're incredibly effective descriptions. The why behind it all is a complete and total mystery.
Which brings us right to Wigner's beautiful and incredibly humble conclusion. He doesn't try to solve the mystery. He just stands in absolute awe of it. He calls this whole thing a miracle, a wonderful gift that, as he puts it, we neither understand nor deserve.
And that's the thought I really want to leave you with. Maybe that old idea from Galileo wasn't just a metaphor. Wigner forces us to ask, is it possible that the universe isn't just describable by mathematics, but that the universe is, in its very fabric, a mathematical structure? And if that's true, what does it say about reality? And what does it say about us, that our minds can somehow tap into that language? That is a question that is still echoing through science today.